So let's talk about the interference of light in this chapter. Okay, so interference is a phenomenon in which two waves superimpose to form a resultant wave of greater or lesser amplitude. So what does it mean? That, for example, we have a wave from passing through this slit. Okay, so this is the small opening, we call it slit, and the other wave passing through the other slit. Okay, this is the slit which is 2, this is slit 1. So in this region, where is the common region, in this region, what will happen? The waves interfere. Waves interfere. Because of this nature, instead of we are repeating, instead of seeing the complete bright, we see a band of region. Say this is the band of region. Say this is the brightest spot. This is the region here. Gap is the darkest spot. So we will see the alternate bright and dark spot everywhere. Okay, so this is again bright. In between two bright, we have the space is dark region. So we also call it fringe. So these spots, these band, bright and dark spot, is also called fringes. Okay, so what will happen? They will superimpose. So this phenomenon is called the interference of the light, because we are considering the waves coming from two sources. Okay, so this wave coming from source 1 and this one coming from the source 2. Okay, and we are assuming that these sources have nearly same frequency of the emitted light, and nearly same amplitude. Okay, this kind of wave we are considering here. So this is the example in the photograph, examples when interference pattern produced by circular water waves in a ripple tank. Okay, so you will see here that the ripples will spread out in the form, and we'll see that two thin plungers are going to vibrate it up and down in phase at the surface of the water. Okay, these are the example. This is the other example. We'll see in the soap bubbles, different colored image. So this colored image is because of the interference of the wave. Okay, so next we'll talk about the coherent sources. So coherent sources produce wave which are in phase or have a constant phase difference, and incoherent source produce wave which have random phase. So for example, say I have a source of, say, source S. This is a monochromatic source. Light means this is the light of single frequency or wavelength. Light with a particular the color. Okay, say for example, this is the light is called maybe red, yellow, green, so whatever, one color. Okay, so let's draw a straight line passing through this, and I make two slits, a small opening. This is slit 1, a small opening, and I make the other a small opening, I call it slit 2. Okay, so this point is S1 and that point is S2. So here S1 and S2 are equidistant. from the source, yes, source of light, yes. Okay, so this S1 and S2 behaves as a coherent source. These are the coherent sources. Okay, so coherent source means they have nearly same frequency. You could write here same frequency, nearly same amplitude. Okay, roughly nearly same amplitude. And third property is in phase or constant phase difference. Okay, so these are called the coherent sources. Let's move further. What is phase difference and the path difference? So phase difference is the difference in phase angle of the two waves. Okay, and path is the path difference between the two waves. Okay, say for example, let's take one example here. Say I have wave first. Say this is started like trough and crest. Okay, like this. I have the second wave. So this wave first, say from source S1. Okay, just like this, we just talked about at that point. And I have the other wave second, say for example, from source S2. Okay, let's just assume, we are just assuming that second wave started from this point. So this means I'm assuming that's like that. Okay, see the difference here. In the above picture, you see that wave first started say 360 degree or 2 pi radian ahead of wave second. Okay, just for example, this is, I'm considering in this example, this is just the case of example here. Okay, so once wave completed one cycle, then second wave started. So we can say that in the word, like we can say like this, say phase means in terms of angle, phase difference between these two waves, phase difference of 2 pi. Okay, 2 pi is equivalent to path difference of wavelength, this value lambda. Say for example, this is the value lambda because this completes one complete wave. So in terms of angle, it is ahead of 2 pi radian. In terms of length, it is ahead of path difference of wavelength value, this value. Okay, so I just write here. Okay, so in the similar fashion, we can say that phase difference of 1 radian is equals to path difference of lambda over 2 pi. Okay, and say in terms of angle, say phase difference of, say, angle delta theta is equivalent to, we are saying equivalent to path difference of lambda over 2 pi times delta theta. Okay, so this is the path difference. So we say in terms of symbol, we can write it is a delta x or delta y, whatever. Okay, so we write an equation in terms of, to convert path difference to phase difference is lambda over 2 pi times the delta theta. Okay, so here the delta x represents the path difference. Okay, lambda is the wavelength of each wave, and delta theta is the phase difference. So we can convert path difference to phase difference and phase difference to path difference by using this equation. Okay, so we can move further about what is the constructive interference and what is the destructive interference. Okay, we can go further with that. So in this picture, you see that first wave crest and crest happens at the same time. You see, for this part, okay, crest and crest is going, so amplitude of resultant wave will be higher. Okay, if it is going trough and trough, the amplitude is going trough, amplitude increases. So this kind of thing where amplitude reinforce is called the constructive interference. In this picture, you see the just opposite. If it is a crest, the other wave has a trough. Okay, we have this kind of thing. So in the second, in the first wave, the crest, the effect of crest is balanced by the effect of trough. So the net intensity will be 0. Okay, so if you see the trough and crest is happening at the same time. So the constructive interference is obtained when identical waves are in phase. So this is called the condition of phase. Okay, they are always in phase. Means the crest happens at the same time and trough happen at the same time. Again, pure destructive interference occurs when identical waves are explicitly out of phase. Okay, so out of phase in the scenario is that, so this is the case of out of phase, means the trough and crest happens at the same time. Okay, so in this picture, say we see that they are going to reinforce each other. So this crest of first wave and the crest of second wave will going to reinforce, so the net intensity will be increased. Okay, similarly, the trough of second wave, first wave, and trough of second wave happens at the same time, so the net trough will be also increased. Okay, but in this case, the crest and trough of two different waves. So this is for the wave first, and this is for the wave second, happens at the same time. So the net intensity will be 0. Okay, so this is the position. In this case, in this kind of situation, we get the bright spot or the bright fringe. In that kind of situation, we are getting the dark spot or the dark fringe. So we see here that in that situation, if the first wave and second wave at a particular point reach and phase difference is equal to the value of this value lambda, then we get the destructive interference. For the constructive interference we are getting at this point, just like before, trough and crest will be at the same point. Okay, so this is the condition for the constructive interference and the destructive interference. So for the constructive interference, path difference could be 0, it could be lambda, it could be 2 lambda, it could be 3 lambda, or it could be minus lambda, kind of thing. Okay, in terms of angle, this is the multiple of 2 pi. So this means it could be 0 times 2 pi, or it could be 1 times 2 pi. Okay, so it keep going like this. For the case of destructive interference, path difference could be like lambda over 2. If I put 1, it will be 3 lambda over 2. This is the case, then we get the destructive interference, and pi corresponds to path difference. This corresponds to the path difference lambda over 2, and phase difference 2 pi, phase difference 3 pi corresponds to 3 lambda over 2. So like this kind of situation, this kind of equation will explain about the constructive interference and the destructive interference. Okay, so this is just the setup of Young's double slit experiment. So here in Young's double slit experiment, we are using the light. It's called the monochromatic light, means light of single color, light of a single color. It could be red, green, blue. Okay, it could be anything. So this is the source passing through the small hole, is called slit. So the light from slit, yes, no, this is the source. Okay, this is the basically main source. It passed on 2 slits of a small opening, S1, S2, and in between the region, interference happen. So we will see the interference pattern. Okay, so let's say interference pattern means this S1 and S2 are 2 slits. So we get, this is the region of maximum intensity, means bright region. So maximum means the position of bright spot or fringe. Minimum means this is the position of dark spot. So we remember from the previous scenario, if this is going to be maximum, first wave, crest and trough, this is for the first wave. Second wave also have crest and trough in the similar fashion. This is the minimum region where intensity is minimum and the spot looks dark. At that position, first wave has wave pattern like this, and the second wave has wave pattern like this. Okay, so they cancel the effect of each other. So this is how we get the interference pattern in the Young's double slit experiment. So I will show you one demo over here about the Young's double slit experiment. Means you see that how the trough and crest intersect. So for example, instead of showing, like say we have the source S1 and source S2, it also generates a wave of crest and trough. It also generates a wave of crest and trough. So in presenting this kind of picture, we are using simply different colors. So for example, this is the so in this case, Say, for example, we can say this is the crest. This is the crest, and down is the trough. If you represent the other way around, we can say this solid line or one color, it represents the crest, and dotted line may represents the trough. Okay, same thing will be here. So you see in this picture that if you have the constructive interference, then this kind of curve, solid, or so solid lines, or dotted will cross. So means trough will be together, crest will be together. For a destructive interference, trough and crest interfere, trough and crest will intersect. So this will be the region of the dark spot. So in this picture, you see that throughout the whole region, either the crest or trough will intersect. So this is the position of central bright. Okay, so let's play these two simulations at first. So let's see the simulation. So here S1 and S2 are two sources. Let's play the animation. Waves are progressing forward and they interfere. Okay, so for example, you will see here that waves are interfering at each other. So if you keep moving, keep going, it will continue to interfere. Okay, then we can show the interference pattern. You see here, central bright, then dark, again bright. This kind of pattern you will see here. Okay, so this is the alternate dark and bright. So if you change the distance between slits, we can do that. Okay, we can change the value of this lambda wavelength. Okay, you can put different numbers. Say I can put like say 700 and then play. What will happen? Okay, so we can change this part. So we can see how interference pattern we'll see in the case of double slit experiment. Okay, and same thing is here in this sketch. You see that if the path difference is lambda, 5 lambda, 2 lambda, we get the constructive interference. Okay, if the path difference is like lambda over 2, 3 lambda over 2, then we get the destructive interference. Okay, next I want to find what is the relation, what is the mathematical relation in the interference. Means in this example, I want to find at the point P, if it is bright, then we want to find the equation. If this is the bright, we want to find the equation in term of this separation between the slit. Say this is D, or we can use any symbol. We can use what is the distance between source and screen. This is the sources. This is called the screen, where we can see the pattern you see in the simulation in terms of D and in terms of lambda. Okay, so our goal is to find the equation. If point P is bright, we want to find what is the equation. If it is dark, or it is the destructive interference, we want to find the equation. Okay, we want to find the equation for that. Okay, this is the main goal. Let's move forward with this picture. Okay, let's define some of the term over here. Okay. So we define some of the terms here. S1, S2 coherent sources. P is the position of this. P is the position of central bright, mth position. C is the position of the. This is the position of the central bright. Central bright. Okay. Why the central bright? Because from these positions, S1 and S2, their point C is at the same distance, equidistance. So if you see S1 and S2, if you consider the point C, the distance, these and these are equal. So this means phase or path difference, okay, is path difference will be 0. If the path difference is 0, this is the bright spot. So this will be the central bright. Okay, and let's define some of the term. Say this point is M. So we define MC. MC is the perpendicular bisector of S1 and S2. Okay, and in this case, you can see that from the picture, or we can assumption, the distance between S1 and S2, which we call it D in this picture. Okay, so we call it distance between S1 and S2, we call it D. Okay, so S1 and S2, we call it D. Is a small, and PM, you see in the picture, PM is much bigger, then we can see from this picture that S1 okay, S1 is perpendicular to S1, not M, S1 N, basically S1 N is perpendicular to PM. Okay, this is the assumption. So from this picture, the key point is this: if this angle is theta by geometry, this angle would also be same angle, theta. Okay, so we can write this as P. We can write this as, okay, let's write here. Okay. Right here is this PMC angle. PMC is angle theta. Then this means we can also say S1 N is also same angle theta. Okay, so you can use our general concept of geometry from triangle S2 S1 N. I can define sine theta, which will be S2 N, which will be S2 N over S1 S2. Okay, so I can write it as just S2 N over, this is the D. Okay, so we know that S1 S2 equals D is the distance between slits. Distance between slits. Okay, slits. Now we can keep moving with our geometry. So from other triangle, from triangle PMC, I can write tan theta equals PC over MC. Okay, so PC from picture is Y, and MC we can say this is the D. So in this picture, you see that MC equals D is the distance between source, or we can say slits, and screen. Okay, is that for a small angle, we can write sine theta is nearly equals to tan theta if theta is small. Okay, this is the small angle approximations. If this is the case, I can write S2, I can write S2n over D equals Y over D. So that gives the relation S2n equals Y D over D. So you know that this is the path difference between the waves. Okay, we end up at this point. So let's move further to our simplification purpose. So we know that P is the position of, we assumed at the very beginning, P is the position of mth bright fringe. Okay, so we assume that if P is the position of mth bright fringe, then path difference we know must be equals to m lambda. Okay, this is from the previous, it is known. So you know that m is equals to 0 or equals to plus or minus 1, plus 2 minus 2. Okay, keep going like this. So this means I can equate two things. So this path difference from this picture is, let's move forward. Path difference is from this equation, and is this also gives you S2n, which is the path difference, is d sine theta. Okay, so this we can use sometimes to solve equations, some problems. This is the path difference. Okay, so S2n we can write here is equals to d sine theta equals m lambda. So now we can equate m lambda must be equals to y d over d. Okay, y d over d. Okay, so for this is our fringe with m. So instead of writing y, we are writing ym equals m lambda d over d. Okay, so I just here write y replaced by ym to indicate mth position, mth fringe or mth bright, only for that purpose. Okay, so this gives the position of mth bright from the position of the bright, central bright. So you see here, so C to P. So this gives what? So you have C here, this is the central bright, okay? You have S1, slit, S2. So the distance between S2 and S2 is D. This distance is capital D. This means if this position P is bright, this distance, we call it YM, position of mth bright fringe. So if you know lambda, D, and D, you can find the position of the bright position. It's called the mth bright. Let's say we have this position. Say I have the other bright. Let's say this is the position of the X bright. So in between, this position will be between two bright. There will be the dark spot also. Okay, this is the position will be bright, dark, position. Okay, so I'm just writing here. If Q is the position of consecutive, say m-1 bright fringe or spot, then we can write y m-1 equals m-1 lambda d over d. Okay, so this gives the one idea is that, let's draw the picture. See, central bright, this point is P, this point is Q, this both are bright, these both are consecutive bright spot. This distance is ym, and we are saying this distance will be ym-1. Okay, so if you want to find what is the difference between two consecutive bright, so we can find that distance between successive bright bands or bright spot or bright fringe, we can use any symbol, say beta. This will be ym minus 1. If you plug those numbers, then we'll find this equals lambda d over d. This is also called fringe width. This is also called fringe width. Okay. Similarly, we can simplify further. By using a dark spot. Okay. So let's see if P is the position of m dark fringe. This is not a bright, this is the dark. Then our phase difference, the part difference, this is the part difference. It will be m plus half lambda. Okay, we have to use this concept where your m will be 0, it will be plus and minus 1 and plus and minus 2. So we can proceed as for the bright spot. Okay, so you will get a similar kind of thing if you repeat the same for this band. If you understand this point, you can answer this question. Okay, so suppose in Young's double slit experiment, two slits are separated by this centimeter. if the third bright line in the screen is formed at an angle of 10.95 relative to the incident beam, what is the wavelength of the incident light? Okay,